This is Lecture 1 of Module 3 in the book Problem Solving Guide for Mechanics and Thermodynamics. Module 3 is Forces. In the previous modules, we described how objects move by determining their position, speed, acceleration, all as a function of time. Where it is, when it is, how fast is it moving, is it accelerating? In this module, we study the forces that produce this motion. A force is basically a push or a pull. That's all it is. If you want to move something, you push or pull on it. One example of a force that we've already discussed in the previous two modules is the gravitational force when we did projectile motion. Gravity pulls on an object with the force mg. M is the mass of the object. G is the gravitational field strength. Little g is the gravitational field strength. F gravity is mg, and we call that the weight of the object. The units of force are mass times acceleration, and if mass is in kilograms and the acceleration is meters per second squared, then we have a Newton after Isaac Newton. The traditional unit of force is the Newton. Gravitational field strength at the surface of the Earth is about 9.1 newtons every kilogram. As before, we call this 10 newtons per kilogram. 10 newtons of force for every kilogram of mass. That's the gravitational field strength at the surface of the Earth. To understand what this means, consider this gravitational field meter. It's a 1 kilogram mass hanging from a spring scale. If the gravitational field is strong, the scale will have a high reading. If it's not too strong, the scale will have a low reading. And it's all with the 1 kilogram mass. At the surface of the Earth, the scale will read 10 newtons. 10 newtons for 1 kilogram. On the surface of the Moon, it reads about 1.6 newtons. The force on a 1 kilogram mass on the surface of the Moon is about 1.6 newtons, so the gravitational field on the Moon is about 1.6 newtons per kilogram. On Jupiter, it's 25 newtons per kilogram. The greater the gravitational field strength, the greater the gravitational pull on a mass. It's that simple. In this module, we'll be using Newton's second law to solve every problem. Here it is. Sum of the vector forces is ma vector. Since we're going to use this equation for every problem, let's really invest some time breaking it down and understanding exactly what it means. The capital Greek letter sigma in this context means sum. So we're going to sum up all of the forces. That's the left-hand side of the equation. The force is a vector, so the vector sum must be taken. If you have a 3 Newton force and a 4 Newton force, and they're parallel in the same direction, they're going to add to 7 newtons. If they're in opposite directions, they're going to add to 1 newton. If a 3 Newton force and a 4 Newton force are at right angles to each other, they're going to add to 5 newtons. The right-hand side of this equation is mass times acceleration vector. What this equation tells us, the magnitude of the sum of the forces must be equal to the magnitude of ma, and the acceleration vector must point in the same direction as the vector sum of the forces. It's a vector equation. The magnitude and direction are the same. So let's make a connection with the previous modules by using the equation F equals ma to determine the acceleration of a rock 3 seconds after we throw it into the air at an initial angle of 30 degrees above the horizontal with an initial speed of 40 meters per second. What are the forces on the rock? Well, we're ignoring air friction, so the only force is the gravitational force. So the left-hand side of the equation, the sum of all the forces is only the gravitational force, and that's mg, and it's downward. The sum of all the forces on the rock is mg downward. We set this equal to ma. The sum of the forces is equal to ma, and we can calculate the acceleration. The masses cancel, and of course the acceleration of the rock is 10 meters per second squared downward. None of that information. The velocity of the rock does not appear in this equation. The initial angle we threw it doesn't matter whether the rock's moving up, down, whatever. If the only force is the gravitational force, the rock is going to accelerate downward 10 meters per second squared, whether it's going up, down, left, right, fast, slow. It could be stopped. It could be at the peak. If it's in the air and there's no drag, it's accelerating downward at 10 meters per second every second. Don't put a velocity force in there. A velocity is not a force. Students love to put the direction of motion on the force diagram. But it has to be a force. You have to tell me where it's from. It's a push or a pull. It's from gravity. It's from friction. It has to be from something. If there's a net force, it's going to accelerate, and it's going to change the velocity vector because that's what acceleration is. So here's a force diagram for the rock in the air, ignoring air drag. It's mg down. It's F gravity. There's no direction of speed. You don't put the speed on there. It could be at rest. Doesn't matter. It's accelerating downward 10 meters per second every second. It's correct irrespective of any motion of the rock. But now let's put air drag in and see what happens. So we drop a 2 kilogram rock off a cliff. After falling for a bit, the acceleration is reduced to 6 meters per second squared by the upward force from the air drag. What is the magnitude of this drag force? Now there are two forces on the rock, the downward pull of gravity, the upward force of the air drag, and it's always a good idea to draw a force diagram. And here it is with the air drag in it. The air drag's upward, the gravity's downward. Gravity's winning because it's accelerating downward. The net force is downward. The gravitational force is bigger. We now use the force equation, Newton's second law, F equals ma. What's the left-hand side of this equation? If you look at the force diagram, it's pretty straightforward. F gravity minus F drag. That's the net force. That's the net force on the rock. We set this equal to ma. That's it. Sum of the forces is ma. Now we just have to plug in some numbers. The force of gravity on the rock is its weight, mg. Its mass is 2 kilograms. The gravitational force is 10 newtons every kilogram, so that's 20 newtons. So there's the weight, 2 kilograms times 10 newtons every kilogram. That's F gravity. There's the drag force, and this is ma. 20 newtons minus the drag force is 12 newtons. This is not a force on the rock. This is the result of all the forces on the rock. It looks like a force because it's 12 newtons, but that's ma. The two forces on the rock are gravitational force and the drag force. This is the sum of the forces. The 12 newtons is the result of the sum of all the forces. So the drag force is 8 newtons. 20 minus 8 is 12. So now let's consider a problem where the forces are in 2 dimensions, but there is no acceleration. If there's no acceleration, the forces must sum to 0. So considering a car going in a straight line at 70 miles an hour, and the net force on it must be 0 because it's not accelerating. There are 4 forces on the car. There they are. They sum to 0. They balance. The car is not accelerating. Let's try to identify them all. Perhaps the easiest is the gravitational force. That's downward. The car is in the gravitational field of the Earth. The Earth is pulling it downward. The reason why the car is not accelerating downward at 10 meters per second every second is because of the road holding it up. And we call that the normal force, the contact force. The tires are contacting the road is pushing up on the tires, and those forces balance. If they didn't, it would be accelerating up or down. Backwards, we have a drag force. The car is plowing through the air. There's a significant drag force on the car when it's going 70 miles an hour. If the car is not accelerating horizontally, there must be a forward force. And the question is, what the heck is that force? What force is balancing the drag force? What is this force? The engine force has to be a force on the car. On the car. What is pushing the car forward? And the answer is the road is pushing the car forward. And it's the frictional force. If there was no friction, that car could not maintain 70 miles an hour against the drag force. The tires are pushing back on the road is pushing forward on the tires, and we have a forward force on the car that balances the drag force. It might be tempting to put a velocity force in there, but velocity is not a force. It doesn't push or pull on the mass. These are real forces: friction from the road, gravitational force, contact force, drag force. Those are all forces. There's a lot more on the frictional force in lecture 2 of this module. For now, let's move forward. Let's consider our two-dimensional problem with no acceleration. But here, the forces aren't going to be orthogonal, so we're going to have to use some trig to break them up into components. So there's a wrecking ball and a crane, and it's pulled well above ground level with an excavator where it's left overnight, so people will have more trouble trying to steal it. So there's the diagram. The cable from the wrecking ball to the top of the crane makes an angle of 25 degrees with the vertical, and the cable from the excavator is horizontal. What is the tension in the horizontal cable? This excavator is pulling the wrecking ball to the right. What is the tension in that cable? There are three forces on the wrecking ball. We always start with the force diagram if we're going to use F equals ma. The cable from the crane, the cable from the excavator, and the Earth's gravitational force. Earth's gravitational force is down. The force from the excavator is to the right, and the force from the cable on the crane is up at 25 degrees from the vertical. There's our force diagram, and those forces should sum to zero because the wrecking ball is just hanging there. The forces from the cables are usually called tensions, and I think we should maintain convention here. The tension in a rope or cable can be imagined just by cutting it and sticking it in a spring scale. This thing will read the tension. If the tension is high, the spring scale will read high. It reads the tension. So we're going to use capital letter T's for tension. So there's the same force diagram, but with T's for the tensions. Some of the forces must be zero in all directions. It's not accelerating in any direction. To make it easier to calculate this tension, let's put the x-axis horizontal and the y-axis vertical, like we normally do. If we do that, then the only force we have to break into components is the tension in the cable from the crane. The components are sine 24 for the horizontal component and cosine 24 for the vertical component. And these here are sines and cosines. These are numbers. These are just percent of the hypotenuse. If the angle is 24 degrees, the opposite side is 40.7% of the hypotenuse. If the angle is 24 degrees, the adjacent side is 91.4% of the hypotenuse. Sines and cosines are just lookup tables for the length of the side relative to the hypotenuse. Now we can redraw the force diagram, and this is why we did it. This is why we broke it up into components, because now it's easy to write the equations. This is where we started. Tc sine 24 is the horizontal component. Tc cosine 24 is the vertical component. What we want to do is we don't want to deal with this. We want to deal with this. Here, it's easy to add the forces and subtract the forces. This is Tc in the y direction. That's T from the cable in the x direction. Forces must sum to zero because the wrecking ball is not accelerating, so we just set the vertical forces equal to zero and the horizontal force equal to zero. In the x direction, we have the tension from the excavator is the x component of the tension from the cable, which is Tc sine 24. That's the horizontal direction. In the vertical direction, we have the gravitational force is being held up. The ball is being held up. The weight of the ball is being held up by the vertical component of the cable. The excavator is not holding up the ball. The excavator's cable is horizontal. And we know what F gravity is. It's the weight. It's 10,000 pounds. So we can solve for the tension in the cable from the crane, just from the vertical direction. There it is. And we get 10,950 pounds. So that's the tension in the cable. That's this guy right here. Now we can get the tension in the excavator cable by using the horizontal direction. Tension in the excavator cable is Tc sine 24, but we just calculated Tc. It's 10,950 pounds. So we can get the tension in the excavator cable 50 pounds, 4,450 pounds. So that's an example of forces that aren't orthogonal. So far we've done a falling rock with no air drag, a falling rock with air drag, falling straight down, a car traveling on a level road in a straight line at constant speed, in other words, not accelerating, and then we just did the wrecking ball. Now we're going to ramp up the complexity one more time by considering a problem with two masses and an acceleration. We have a 3 and a 5 kilogram block attached via a light rope that goes over a light pulley and turns without friction. So there's the 3 on the left, there's the 5 on the right. We let this go and the 5 is going to accelerate downward. The 3 is going to accelerate upward. What is the tension in the rope that connects them? There's an acceleration here, so the forces aren't going to balance. In physics, as always, the goal is to make solving the problem as easy as possible. When we did projectile motion, we considered one direction at a time, the x direction independently of the y direction. And here we're going to consider the 3 kilogram block independently and the 5 kilogram block independently. There's a lot going on. We're going to focus only on one block at a time. We're going to do F equals ma for each mass. The net force on the 5 kilogram mass is ma for the 5 kilogram mass. The net force on the 3 kilogram mass is ma for the 3 kilogram mass. One at a time. Let's do the 3 kilogram mass first. What are the forces on the 3 kilogram mass? There's two forces. The tension is pulling it upward. The gravitational force is pulling it downward. The tension is winning because the 3 kilogram mass goes up. The 3 kilogram mass does not know about the 5 kilogram mass. The only thing the 3 kilogram mass knows is the rope. The rope's pulling on it. Gravity's pulling on it. These are the forces on the 3 kilogram mass. We know tension is bigger than gravity. It's accelerating upward. The gravitational force on a 3 kilogram mass is mg, and that's 30 newtons downward. So we have 30 newtons pulling downward, tension's pulling upward, and tension's winning. So we know the tension must be bigger than 30 newtons. We can write the equation, F equals ma. The sum of the forces is T minus F gravity. That's ma, and we know what the mass is. It's 3 kilograms. This is only on the 3 kilogram mass. There's nothing to do with the 5 kilogram mass. We have two unknowns, the tension in the rope and the acceleration. We need another equation, and we get that by isolating the 5 kilogram mass. Here's the force diagram. Gravity's down, tension's up. It's very similar to the 3 kilogram mass, but in this case, gravity's winning. It's accelerating downward. It's heavier. The gravitational force is 50 newtons downward, so we know the tension must be smaller than 50 because the 50 is winning. Now we write F equals ma for the 5 kilogram mass. And we can plug in what we know about the 5 kilogram mass. There's the sum of the forces, F gravity minus tension. It's accelerating downward. And for the m, we put in 5 kilograms. We're doing F equals ma for the 5 kilogram mass. Now we have two equations, two unknowns. There's the 3 kilogram, there's the 5 kilogram. F equals ma for both of them. We have two equations, two unknowns. We can solve this. We put on our math hat. We're asked for the tension, so we solve for A. In the first equation, substitute in the second, or vice versa, it doesn't matter. So acceleration is t minus 30 over 3 from the first equation. Just subtract 30. No, just divide both sides by 3 to get A. That's all we have to do. That's A. Stick it into the second equation, and we get T is 37.5 newtons, which is good news because it's bigger than 30 and less than 50. For completeness, let's get the acceleration, even though we weren't asked for it. The acceleration is T minus 30 over 3 as we solved, and we know T is 37.5. So the acceleration is 7.5 newtons over 3 kilograms, which is 2.5 meters per second every second. The 3 kilogram mass is accelerating upward, 2.5 meters per second every second. The 5 kilogram mass is accelerating downward at 2.5 meters per second every second. Let's check to see if this makes sense. Let's see if indeed F equals ma. The 3 kilogram mass is being pulled upward by the rope with a force of 37.5 newtons. Gravity is pulling downward with a force of 30 newtons. That's a net of 7.5 newtons upward. The net force on the 3 kilogram mass is thus 7.5 newtons upward, and this is equal to ma for the 3 kilogram mass. Because the mass is 3 kilograms, the acceleration is 2.5 meters per second squared. Now let's shift our attention to the 5 kilogram mass. The 5 kilogram mass is being pulled upward by the rope with a force of 37.5 newtons. Gravity is pulling downward with a force of 50 newtons. That's a net of 12.5 newtons downward. This is equal to ma for the 5 kilogram mass, because we have a 5 kilogram mass accelerating at 2.5 meters per second every second. 5 times 2.5 is indeed 12.5. So everything checks. So let's tackle a two-dimensional problem with two masses and a frictional force. So we have a 5 kilogram mass connected to a 2 kilogram mass via a rope. The pulley turns without friction. The 5 kilogram block is accelerating downward at 4 meters per second every second. What is the frictional force between the 2 kilogram block and the surface along which it is sliding? The angle of the plane is 25 degrees. As before, we isolate the two blocks. Identify the forces on each, set the vector sum of those forces equal to ma for each mass individually. Let's start with the 5 kilogram block. We have a 5 kilogram block, we have gravity, and we have tension, a rope attached to it. Gravity's downward, tension's upward, gravity's winning, because in the problem it says the 5 kilogram block is accelerating downward at 4 meters per second each second. The sum of the forces is F gravity minus T, as can be seen from the diagram, and we set that equal to ma with the mass at 5 kilograms. So the sum of the forces is 50 minus T, because it's a 5 kilogram mass. The gravitational force is 50 newtons, and we have ma that's given. Ma is 20 newtons. This is the sum of the forces. This is the result of the sum of the forces. 50 minus T is the sum of the forces, and ma is 20. So we know what the tension is. The tension is 30 newtons. 2 kilogram block is a little bit more complicated. It's on a plane that's inclined at 25 degrees. There are four forces on this block. We have gravity, which is straight down. We have the tension, which is pulling it up the plane. And we know what the tension is. It's 30 newtons. We have friction, which is back. The 2 kilogram mass is grinding along the surface. That's kinetic friction. And we have the normal force, which is perpendicular to the surface. That's why it's called the normal force. It's normal to the surface. Those are the four forces. The block is accelerating up the plane. It's convenient to define the positive x-axis in the direction of the acceleration up the plane. So we're going to tilt the axes here. As a result, the acceleration of the block will be the acceleration in the x direction. And the acceleration of the block in the y direction will be 0. If we kept the x and the y-axis horizontal, we would have to break the acceleration into components. And we don't want to do that. Let's not make it any more complicated than it has to be. It's already complicated enough. So we're going to put the x-axis along the acceleration, and the a sub x will be the acceleration of the block. So the sum of the forces in the x direction, which is along the plane. The tension is up, pure x. The friction is pure x backwards. And then we have the gravitational force, which is pulling it down the plane. Gravity's pulling this block down the plane. There's a component of gravity pulling it down the plane. So for now, we can write F gravity in the x direction, but we have to calculate what that component is. And here it is right here. How big is this piece? That vector is mg. How big is that component? So let's add a horizontal line. And we know the angle of the plane is 25 degrees. So that angle is 25 degrees. If that's 25, this is 65. And this is 25 right here. So it's mg sine 25, the opposite side. So now we know what the component is. So now we can write sum of the forces. Tension is up the plane, friction is down the plane, F gravity sine 25 is down the plane, and that's ma sub x for the 2 kilogram block. The forces on the 2 kilogram block in the x direction is ma sub x for the 2 kilogram block. There's the equation. We can substitute in what we know. The weight of the block is 20 newtons, mg, and ma, we know that the acceleration is 4 meters per second squared, and the mass is 2 kilograms. We can plug some numbers in here and get 8.5 newtons. The tension is pulling the 2 kilogram block up the plane with a force of 30 newtons. The unknown friction force is down the plane. The component of gravity down the plane is 8.5 newtons. The result of all of this is 8 newtons up the plane. That's the sum of the forces. That's the result of the sum of the forces. That's ma. So we can calculate the frictional force with some algebra. It's 13.5 newtons down the plane. So now let's get the contact force. In the y direction, there is no acceleration. The bonus that we get for putting the x-axis along the plane is that we get that the forces balance in the y direction. The only force in the positive y direction is the normal force, and there's a component of gravity in the negative y direction. F gravity cosine 25 degrees. And those balance because it's not accelerating perpendicular to the plane. And we can calculate it's 18.1 newtons. So now we have these four forces. 30 newton tension, 20 newtons gravity, 18.1 newtons normal force, 13.5 newtons frictional force. And this is why we break up the 20 into its components, because we can really see what's going on. So let's break up the 20 newton gravitational force into its x and y components, and we get this. So the 18.1s in the y direction cancel. We have a positive 30, and then we have 13.5 backwards and 8.5 backwards. That's 22 backwards, which is a net of 8 up the plane. This is why we define the x direction along the acceleration. We know the net force is along the x direction because that's the way it's accelerating. Finally, before we go, let's construct a head-to-tail addition of these four vectors. These four vectors on the left: gravity, friction, normal force, tension. We're going to add them head to tail. So there they are. These four vectors, when we add them head to tail, it must be 8 newtons along the positive x-axis. So now we're going to move over the the gravitational force at the end of the tension. So we're just doing head to tail. Now we're going to put the frictional force at the end. Now we're going to put the normal force at the end. And if we add all those up, we get this. That's the net force. That's ma. That's 8 newtons along the x-axis. Now it's your turn. Do some problems.